Okay. Here too we have negative energy states, but Dirac could explain it successfully. So from Klein-Gordon equation, the energy is given by this equation, which we know already. This replacing E by IH cross d by dt and P by minus IH cross d, corresponding operators, and allowing this equation to operate on the wave function. Okay. So now we are going to substitute E for this operator, expression for operator, and P for this operator, and we are going to allow this equation operates on the wave function, and we will get this 8.43. So Klein-Gordon equation becomes exactly like this. Okay. Now this is second order. Okay, this is second order. Throughout we have second order differential equation. But Dirac looked for an alternative which was the first order throughout. He used eigenvalue equation and he boldly wrote this equation. So C times alpha dot P plus beta MC squared, which acts on psi, which is equal to HSI equal to E psi, IH cross d psi by dt. Now look at P can be replaced with minus IH cross d by partial d by dx. Look at the left hand side, it is d by dx. Look at the right hand side, d psi by dt. See, first order in time in space. Okay, Lorentz invariance, it will work out. Okay, it's symmetry in space and time. Space and time. Where H is a Hermitian operator, and as usual P equals minus IH cross del. Now from equation 8.42, special of relativity, we know that E squared equals C squared P squared plus M squared C power 4 acts on psi, which is equal to 0. Okay, just I bring the right hand side term to left hand side, I can write this equation, and this equation is multiplied with this. In order to obtain the similar equation, we are going to multiply equation 8.44 by this term. Okay, we are going to multiply with this term. I repeat, so this is equation 8.44, correct? This is the equation. This is the equation. IH cross d psi by dt. Okay, this equation can be written as, this is your E. So this equation can be written as E minus this equation. I am going to multiply this equation with E plus. Is it okay? I repeat. See, you have Dirac's equation, which is equal to E. So this equation can be written as E minus this term. I am going to multiply this equation with E plus. E plus. That's the idea. So you have E minus is this side, you have E plus is this side. This is equal to 0, which is nothing but your equation 8.46. Multiplication is very simple. We will look into. Now E multiplied, first thing is we will go with the alpha dot P first. As I said, alpha will have 3 components. P also will have 3 components, Px, Py, Pz. So this becomes alpha x, Px plus alpha y, Py plus alpha z, Pz. The first term, that's all. Minus the same beta MC squared, and this can be expanded in terms of components, plus beta MC squared. Now we are going to multiply these two. Okay, multiplication is very simple. We will find out. E multiplied by V will give you E squared. First one. Beta MC squared multiplied by beta MC squared will give you minus beta squared M squared C power 4. Okay, we have finished the extreme ends of the equation. Now we are going to multiply this term with this term. Okay, this term with this term, this term with this term, this term with this term, and take the common term out. So C multiplied by C will give you C squared. Your alpha x multiplied by alpha x will give you alpha x squared. Okay, Px multiplied by Px will give you Px squared. The first point is over. Similarly, this multiplied by this will give you this term. This multiplied by this will give you this term. So second part is over. The second part is over. Okay. Now the third part. I am going to multiply this term with this term with this term, and take the common term out. Okay. So this term multiplied with this term will give you alpha x, alpha y. This term multiplied with this term will give you again alpha y, alpha x. Okay. What are Px, Py? Px, Py equals Px, Py, Px. Okay. So I can take Px, Py common out. So that's the idea. I repeat. Alpha x multiplied with alpha y multiplied with alpha x, and we have px, py, px, but px, py equals py, px. I can pull px, py out. Second is over. See here, alpha x, alpha y plus alpha y, alpha x, px, py. Of course, this will have minus c squared. So that part is over. Now I am going to multiply this term with this term and this term with this term. Take py, pz out. So this term will be alpha y, alpha z, alpha z, alpha y with a common term of py, pz. See, py, pz. The next one is this term multiplied by this term multiplied by this term. The first one was these two terms. Second one, these two terms. Third one, this term and this term. See, this term and this term we have written px, pz. See, pz, px. Of course, last term we have already mentioned. Any doubt? This equation? Okay, any doubt? Now you go for the rest of the terms. This multiplied by with all the term, this multiplied by with all the terms. That's the last one. So beta mc squared, already one c is there. You have to multiply with the c, so that will give you minus mc cube. Okay, mc cube. What about next one? So you have alpha x beta. So either way you can do it. So this can be alpha x beta. So alpha x beta. So this must be beta alpha x. See, beta alpha x. Alpha x beta plus beta alpha x. What are the common term? So we are going to multiply this one and this one. Common term will be your px plus next term will be alpha y beta plus beta alpha y. Common term will be py. Alpha z beta plus beta alpha z. Common term will be bz, which operates on psi which is equal to 0. Is it okay? This equation. We know this equation earlier. C squared minus E squared minus C squared P squared plus M squared C power 4 acts on psi equal to 0. We are going to compare this equation with this equation. He compared this equation with this equation. Look at the equation. We have E squared. E squared is there. M squared C power 4. M squared C power 4. Your beta squared is there. You compare first and last term first. So E squared can be compared, and M squared C power 4, this will be compared with beta squared M squared C power 4. So beta squared must be, what are the beta squared? Beta squared must be equal to 1. Only then we can compare the equation. Is it clear? I am going to compare this equation with this equation. And look at the first term. It will be E squared. Here also you have E squared. We have beta squared M squared C power 4. You compare this one. So beta squared must be equal to 1. That's only one possibility. What about this term? This term. We will compare with this second one. We have C squared. We have C squared P squared. Here we have alpha x squared px squared plus alpha y squared py squared plus alpha z squared pz squared. Here we have only p squared. So what about alpha x squared? It must be equal to 1. Alpha x squared must be equal to 1. Alpha y squared must be equal to 1. Alpha z squared must be equal to, only then this will become your p squared. So p squared is equal. What are the remaining terms? Alpha x alpha y plus alpha y alpha x. This must be equal to 0. Very good. 0. This must be equal to 0. This must be equal to 0. Is it okay? So we have concluded that first one, beta squared, which is equal to 1, alpha x squared equal to 1, alpha y squared equal to 1, alpha z squared equal to 1. That's very clear. And second one, this must be equal to 0. If it is equal to 0, alpha x alpha y plus alpha y alpha x equal to 0. AB plus BA equals 0. So AB equals minus BA. So A and B are anti-commute with each other. That's the idea. And this also will be equal to 0. Okay. So that's a conclusion. Very important conclusion he made was, as I said just now, alpha x squared equal to alpha y squared equals alpha z squared, which is equal to beta squared equal to 1. And they will anti-commute with each other. So this is equivalent to 0. Similarly, alpha x beta plus beta alpha x also equal to 0. So alpha x beta equals minus beta alpha x. Alpha x and beta both will anti-commute with each other. So all alphas and beta, they will anti-commute in pairs and their squares are equal to 1, unity. That's the conclusion. So those properties immediately suggest that they cannot be numbers, as I said, because they will commute. Numbers will commute. As I said, 3 multiplied by 4 equals 4 multiplied by 3. Numbers will commute. Okay, but matrices will not commute. They will anti-commute, especially Pauli's matrices, which we have seen. So those properties immediately suggest that they cannot be numbers. Already we have seen we have a set of anti-commuting matrices like Pauli spin matrices. Hence it's convenient and express them in terms of matrices. Okay, the energy can now be written as, okay, now the energy can be written as exactly in this form. I have pulled C out. Okay, in the earlier equation, C alpha dot P plus beta mc squared. I have pulled one C out. So your Hamiltonian, this is called Dirac Hamiltonian, and the energy equation is given by this equation. The positive and negative sign can be taken since replacing alpha by minus alpha and beta by minus beta does not change the relationship between alpha and beta. So this is called a Dirac Hamiltonian. Okay, so as I said, alpha, it's a vector operator, beta is a scalar operator. It must be this is mc squared, it's a value. Okay, it's a scalar quantity. Okay, so in terms of matrices, we can write beta as eigenvalue numbers like 1, 0, 0, minus 1. So beta can be written as eigenvalues 1, 0, 0, minus 1. Okay, diagonal elements. Only diagonal elements will exist. 1, 0, 0, minus 1 for beta. So replacing E and P by their operators and allowing the resulting operator equation to operate on psi of r comma t, we have this. So h psi equal to E psi. So you have E psi is given by this. Just replace with the operators. See, just replace with operators. You will have this. Left hand side you have E. So which is nothing but I h cross d psi by dt. Look at the equation now on both sides. Single derivative in terms of space coordinate, single derivative in terms of time coordinate, symmetry in space and time. Okay, covariance of Lorentz transformation. See, invariance of Lorentz transformation. It's very clear. So equation 8.52 is the Dirac relativistic equation of a free particle. So this is the second equation, second relativistic equation which we have seen now. Here alpha and beta are the matrices of the same order. Any doubt? Okay, now we will be dealing with Dirac matrices. So as I said earlier, alphas and beta. Beta is always will have diagonal elements 1, 0, 0, minus 1, 1. Your alpha x will be Pauli's matrices. And there must be some properties of Pauli's matrices. Of course, we have seen that Pauli's matrices are anti-commuting matrices. So we know. The second main property will be your Hermitian property. Only then you will have real eigenvalues. It must be Hermitian. It must be Hermitian. Only then you can have real eigenvalues. Okay. Then another property will be trace property. That's all. So the first one, Dirac matrices anti-commute in pairs. Squares are unity. Alpha x squared plus equals alpha y squared equal to alpha z squared equals beta squared equal to 1. So the squares are unity. The operators in the Dirac Hamiltonian have to be Hermitian. Only then we can have real eigenvalues. So it must be Hermitian. Alpha equals alpha x dagger. It's an operator. Okay, it's an operator. So alpha x dagger. Alpha y equals alpha y dagger. Alpha z equals alpha z dagger. Similarly, beta equals beta dagger. So as every Hermitian matrix is square, therefore Dirac matrices alphas and beta must be square matrices. So we are going to deal only with the square matrices. Okay, all will have only square matrices. Hence the squares of the eigenvalues of all the four matrices will be always plus or minus 1. We can see since the square is unity. So we have now the next property is about the trace of the property. Trace of the property is nothing but adding the diagonal elements of a matrix. We know already. So when you are going to add the diagonal elements, for example, as I said, your alpha z will be 1 0 0 minus 1. What is the trace of the matrix? It is 0. 1 plus minus 1, it is 0. What about beta? Beta equals 1 0 0 minus 1, just now I said. So add the diagonal elements, that will give you trace of a matrix, which is nothing but 0. Okay, what are the rest of the matrix? That also we will find that it will be 0. Okay, we will come to know. Now we can write alpha x as alpha x beta squared, because beta squared equals 1. We are going to find out the next property, third property, which is nothing but trace of a property. So alpha x equals alpha x beta squared, because beta squared equals 1. Beta squared can be written as beta beta. I am going to interchange with the minus sign. AB is not equal to BA, so I am going to interchange. When you are going to interchange, this must be minus beta alpha x beta. Is it okay? Now I am going to find out the trace of first and last term, which is nothing but trace of alpha x equals trace of minus beta alpha x beta. I am going to use this identity. This identity, trace of ABC equals trace of BCA, trace of CAB. I am going to change this one. See, you have ABC. Pull minus sign out. So this becomes alpha x beta beta. Is it okay? I am going to use this identity, ABC equals BCA, which is equal to CAB. So I am going to interchange this one using this identity. So this becomes minus trace of alpha x beta beta. So beta beta is nothing but beta squared, which is nothing but 1. So minus trace of alpha x. So trace of alpha x equals minus trace of alpha x. So that will become 2 trace of alpha x in bracket. 2 trace of alpha x, which is equal to 0. Is it okay? 2 cannot be equal to 0. Only trace must be equal to 0. So trace of alpha x equal to 0. It's very clear that trace of alpha x equal to 0. Similarly, you can prove for trace of alpha y equal to 0. Trace of alpha z equal to 0. That's why I said you add the all diagonal elements, it will become 0, 0. Because trace of alpha x equal to 0. Is it okay? Very, very important property. Another property. So it is evident that on equation 8.56, trace of alpha x equal to 0, which is possible only when the number of plus 1 eigenvalue is equaling number of minus eigenvalue. Okay, so this restricts the dimension of alpha x to an even number. These results are applicable to alpha y, of course, as I said, applicable for alpha y, alpha z and beta. Okay, we have done only for alpha x. This is applicable for rest of the things, alpha y, alpha z and beta. So as I said, Dirac matrices are even dimension 2 by 2. The next one will not be 3. We will have to go only with 4 by 4. We are going to see now. So and so on. Since alpha x squared plus equals alpha y squared equals alpha z squared equals beta squared equal to 1, therefore the eigenvalues of matrices must be equal to plus or minus 1. No other way. Since all the matrices anti-commute, therefore only one of 4 matrices will be diagonal, that is beta. So that's why I said beta will be a diagonal matrix. So beta we have taken as diagonal matrix. We know that we have already 3 anti-commute and 2 by 2 matrices, which are Pauli matrices, alpha x, alpha y, alpha z, and which are given as alpha x is given by this matrix, alpha y is given by this matrix, and alpha z is given by this matrix. As I said, easy to remember is 1 minus 1. Can you remember? One is spin up and another one is spin down. So 1 0 0 minus 1. Similarly, you just find out this one, that is anti-commuting of sigma x, sigma y plus sigma y, sigma x. What is the value? You just find out. Use these matrices. You find out what will be the value, and you can easily see just substitute for sigma x, which is nothing but this matrix, sigma y for this matrix. You find out the answer, and you go for sigma y, sigma x. You find out the answer. Whether you will get exactly minus with a minus or not, you just find out. Okay, the square of each of these matrices is unity, we know already. You also find out sigma x squared, which is this matrix multiplied by the same matrix. Answer is 1 or not, you just find out. So this will become 1 0 0 1. Similarly this one also, this one also. So it can be shown that fourth matrix that anti-commutes with each with these 3 cannot be found. Okay, The next possibility is n equals 4. As I said, when you are going for 2 by 2 matrix, next possibility only 4 by 4 matrix. Okay, and beta matrix is taken as a diagonal with 2 plus 1 eigenvalues and 2 minus 1 eigenvalues. For 4 by 4 matrix, we will have 4 eigenvalues. Okay, so 2 will be for plus 1 and 2 will be for minus 1. So we have 3 Pauli's matrices, as I said, sigma x, sigma y, sigma z, satisfying all the above properties, 4 properties we have seen just now, but we cannot have such fourth 2 by 2 matrix. So next possibility is getting 4 by 4 matrix. So how to go with 4 by 4 matrix? You have alpha x equal to 4 by 4 matrix I have written. You just consider this is your sigma x. Pauli sigma x matrix. You consider this must be your sigma x again. So we can write this alpha x equal to 0, sigma x, 0. This is 2 by 2 matrix. Okay, we have converted 2 by 2 matrix. This is 4 by 4 matrix. This we have taken as alpha x. This we have taken as alpha x. Similarly, you can go for this must be your alpha y. This must be your alpha y. Similarly, this must be your alpha z. So this must be alpha z. So there is a relation between alphas and sigmas. Okay, similarly beta as I said, so this is your beta. Okay, 1 0 0 1, see minus 1 minus 1. As I said, for 4 by 4 matrix we will have 4 eigenvalues. Just now I said 2 plus 1 and 2 minus 1. Just now we see this can be written as I 0 0 minus 1. So clearly these matrices are Hermitian. All the matrices are Hermitian, since alpha x, alpha y and alpha z are Hermitian. Any doubt? Okay, any doubt? The matrix is given in equation 8.58 to 8.61. 8.58 to 8.61 are Dirac matrices. Okay, the heading is Dirac matrices in the standard representation. Since alphas and betas are 4 by 4 matrices, Dirac's wave function is given as 4. See, it's a column vector. Psi 1, psi 2, psi 3, psi 4. So it's a column vector. And this can be written as a complex conjugate of this. This can be written as a row vectors. So row vectors and column vectors, your psi star. See, above equation 8.62 is referred as Dirac spinors. The counterpart of Schrodinger equation is Dirac theory 4 by 4 matrix. So in this section we discussed in detail about the Dirac Hamiltonian. It's not derivation, but Dirac postulated the Hamiltonian, which is symmetry in space and time with a single order, with one order. Okay, either side you have d psi by dx and d psi by dt. Okay, either. Okay, single order. And we are looking detail about Dirac matrices. Okay, so we will wind up today. We will see in the next class.